I'm inside PixInsight now, and the first thing I'm going to do is just load some of the icons that I use on a regular basis. This is a feature of PixInsight. You can organize settings and icons, and those will appear over here. And I'll explain each one of these, but these are sort of the things that I use for my workflow. And let me just do arrange icons to bring them over so they're visible. Now we're going to go open that file that has the Monkey Head Nebula. And that's going to be this one. It's 2 sessions. It was 365 fits that we processed. And the first thing I do is I go into my stretch tool, and instead of using the regular stretch, I use the extreme stretch. This one here, the boosted. This really draws out details and artifacts. Like you can see this noisy zone, you can see this. So what I want to do is crop this and get rid of all the noisy sections. So I'm going to do dynamic crop. I'm just zooming out so I can see my edges. Then I'm going to take this and just grab it and drag it down. I'm going to take this and drag it over. Take this and drag it over. And finally bring this up. So I'm just framing this and getting rid of all the noisy sections, kind of trimming off the excess. Now, one of the things you can do is sometimes you'll see these come in tilted. You can actually crop at a diagonal if you want to. We don't need to for purposes of this. So we're going to go ahead and do this and take our dynamic crop tool, click the check mark, and we have it cropped. Now, normally what I would do is I would look at some existing images of this nebula and make sure it's oriented in a way that's a common way or something that I can reference. Here I can clearly see the monkey head as is, so I know it's oriented correctly. So I'm going to go ahead and move the stretch back down. So this is the normal stretch, and we're actually at a pretty good starting point. Now the first decision to make, the first thing I always do is I get rid of the background. And you can either do that with automatic background extraction or dynamic. Now if it was dynamic, we'd have to make a ton of squares and make sure that they basically represented places that are pure background. And I can actually show you what that looks like. So let's do this. Let's make a copy of this. And first I'm going to show you automatic background extraction. So that's this. And the way I've got it set up, I'm going to open it so you can see the settings I have saved. It's pretty much the defaults, except that I'm doing subtraction. Discard background model, replace target image. I don't care about seeing the background model. I can tell if it looks good or not. If this had a vignette, which meant like it was radiating out, if it was a circular pattern of light pollution, I would do division. But because it's pretty uniform, I'm doing subtraction. So that's what the dialog looks like. I literally just drag this and drop it and let it process through. So we can see in the output window the steps that it's taking. And then we get something that we have to restretch because it changed the parameters on us. And that's what it looks like with the automatic background extraction. So we're just going to sit on that for a second. And then we're going to come to the copy of our image. And we're going to look at the same process using dynamic background extraction. I'm pretty sure I'm going to just stick with automatic for this, and it's a lot less effort. But I want to show you dynamic if you have to do that. So here's dynamic. The key here is going to be on sample generation, kind of my sample size. So if I drop one in, that square is pretty good size. I might want to tweak it a little bit bigger. I try to get as big as I can and still fit multiples in the display. So let me actually take this to 70. And then if you drop it on a star, this is what you get over here, is this huge black indicator that it's in a star. We don't want that. We want it pure background. We also don't want to drop one here, which is part of the nebula. Now at the edges, you can decide kind of how diffuse you want it to be. But basically the idea is to get as many of these as possible without capturing stars or nebula. Bonus if you can get it right on the edge, like we'll move this one over. And it's okay to have these overlapping. I can do that, and that's perfectly fine. These are just samples that it uses to get a statistical representation of what the background looks like. And then from that, it can compute a model that it can subtract. Now, I said that I'd discard the background model, but for this round, I'm actually going to keep it just so I can show you what it looks like, so you can see kind of what the mechanism is. Now, I've got a decision to make here. There's probably faint nebulosity here that we can either contrast out or we can keep. I think we're more concerned with the main details of the actual main part of the nebula, so I'm not as concerned with faint nebulosity over here going away. So I'm just going to keep clicking and adding these and not worrying too much if this is a faint little bit. And you can see like this star's kind of shrouded and this one is, so that implies that there's still some nebula in between. So I might go a little bit farther out, kind of trace a semicircle around here to kind of guide where I'm going to place these other items. Now there's debate over how many of these you need. I really don't try to get to a specific count. I try to cover as much background as I can that is true background, and especially with variations, like you can tell it's getting darker here as we get closer to the edge. And so I want to make sure that I capture those variations as well. So I'm going to keep clicking. This is a tedious process, this one, and actually creating a point spread function, which we'll cover later. But I feel like I have a pretty good representation of the background now. So here on target image correction, I'm going to tell it to keep the background model so we can see what that looks like. And then I'm going to click the checkbox. So hopefully, if things go right, all of your squares turn red, which means they're no longer valid background, which means it subtracted it out. Now here's the background model. And to see it, like with everything else, we'll need to stretch it. So I'm going to go ahead and stretch. And so you can see that's kind of the pattern that it subtracted out. And then if we look at the result, this is what we get. So I'm going to align it with the other, and then let's take a look at this versus the automatic. So in my opinion, the automatic did a much better job of clearing it out. We've got some around the edges, but the central piece, which is what I'm more concerned with, did better. So I'm going to throw away that dynamic that we did and start with that. So that was the first step, was getting the background sort of extracted to get rid of that first layer of noise. Now I need to neutralize the background to make it as uniform as possible. So to do that, I want to find a piece of representative background and create a preview. So I'm going to zoom in, because I believe over here on the right side, we can find an area, probably, I'm going to guess right in here. So I'm going to click on my preview icon and try to make as big a square as possible without grabbing stars. And it's okay for these previews to be huge if you have an image that doesn't have a large star field. But this size should be good. So now I've got something that's representative of my background. I'm going to keep that because we'll use that multiple times. So I'm going to go into background neutralization. And I don't mess with the settings. There's actually some ways you can tweak these limits. I'll admit I'm not the best at that. So I go just for the straight defaults. I grab that preview and I click this, or you can drag this to apply it. And now the background's neutralized. It was very subtle. It probably didn't show up in video, but something did happen. Finally, for background and color, the next thing I do is color calibration. Again, there's two ways that you can do color calibration. So again, I'm going to make a copy and show you the difference. Probably the easiest way is to go into the color calibration tool. And what you're going to need is two things. You're going to need a preview that represents the background. So we'll kind of, it's not the exact same preview, but it will be good enough. And it looks like I captured the edge of a star. So let's zoom in and tweak that just slightly. And then review it. So that is background. So you want background, and then you want a second preview window that represents stars. Now you can use the whole image as a reference. I like to take something that I believe is going to be sort of a bright set of representative stars. So I'm going to just take this section right here because we have a few different colors and we have some clustered, etc. And so then we go into our color calibration dialog. And we reference our white reference, which is going to be that second preview. And this is in the clone. And then structure detection just means it's going to look inside the preview, find the stars, and look those up. And then we have the background reference. So for the background reference, I'm going to take that preview 1 on the clone, and then I'm going to go ahead and run that. And this is the result. Notice our background now looks dark. Our nebula still has some nice color, but it's really taken those two extremes and it made the background black like it's supposed to be, and it made the stars the star colors. So that's color calibration. The other way you can do it is you can use photometric color calibration, and this one actually goes to a database of known colors. So some people consider it more accurate, but it also is a little more nuanced. Because what I have to do is I have to know the focal length. I have to know my pixel size. Now my pixel size is 2.4, but you have to be careful here because I did that bare translation, that dithering. So I made it 3 times the resolution. So that means it's 1/3 of the pixel size. So I actually have to divide this by 3 and make the pixel size 0.8. I'll put the date of the most recent observation, and then I need a right ascension and declination. So we know that this is NGC2174, so we can search for that, get the coordinates, and now we should be ready to go. What it's going to do is it's going to do something called plate solving, which is figuring out what the actual dimensions of this are. Then it's going to find a database of similar images and use those to calibrate the stars. So let's bring in our process, our console, and let's apply this and watch it go to work. So the first thing it's doing is it's using catalogs to try to figure out what the actual coordinates of the image are. Because this was stacked, the coordinates don't come over because each frame is slightly different from the other frames. So it has to plate solve this. Now it's successfully plate solved. So now what it's doing is it's going out and finding other images in the database. Sometimes it has to download these. And it's matching it up to the stars in our field of view, and it's making computations based on what the intensity and the color and saturation and other characteristics are. And then it's going to apply some transformations to normalize the colors. The same way color calibration did except while color calibration used the photo itself to calibrate, this is using a database. So we'll let it run. Sometimes it takes a while. This is a pretty big image, so it takes a little bit longer than if you were working with a smaller image. But I'll let it run and we'll see what the result is. Okay, it has finished and it shows that it processed and applied everything. So we're going to move this out of the way. We're going to close this. And this is our final result. And again, a nice dark background, colorful foreground. Let's do the same thing and take a look at our clone and our regular one. I like the saturation in the clone better. It's a little bit richer color, a little more dynamic. So I'm actually going to go with this. So I'm going to close this main image and we're going to move forward with this clone. And the next step that I'll work on is called deconvolution. The next step in our linear processing, or the initial processing, is deconvolution. Deconvolution attempts to address issues created when you're recording the photograph, and things like turbulence in the atmosphere and bad tracking throw the stars out of shape. Stars should be perfectly round, ideally points of light. Now you can see, if I zoom in, these are pretty good star shapes. They're not too stretched out, but it can always use improvement. Now there's a lot that goes into deconvolution. I'm not going to get into all of it, but I will share a script that I use to generate sort of the support to get started. So this is, again, the Deep Sky Workflows website. Go to Scripts and Tools. This time we're going into Deep Sky Workflow Scripts. And this is a set of scripts for PixInsight that provide various services. The one I'm looking at is generating decon support. There's instructions here on how to install the scripts, so I won't get into that, but let's go ahead and run it and see what happens. So I'm going to do script, Deep Sky Workflows, generate decon support. Now here it's got to create a stretched luminance channel from the image. And so I give the opportunity to select existing if a mask has already been made or the channel's already been made. We haven't done that, so these are both checked. We can generate a star mask, which is recommended because you want to only apply deconvolution to the stars and nothing else. This will use StarNet to extract the stars from the image, and then it'll use morphological transformation to grow the stars, and convolution, which is the opposite of deconvolution, to blur them so that there's a less of a harsh edge to the star mask. One key part of deconvolution is the point spread function. That is an image that represents the distortion of the star that's used by deconvolution to correct it. There's two ways to create a PSF. One is through a script that you can download, and that script basically scans and generates, or you can select them yourself using dynamic PSF. What this setting does is it sets up a special mask to make it easier to select the right stars, and we'll see what that looks like. And I'll talk about decon settings as well. The goal of this script is to get everything set up and basically just leave you with the step of creating the point spread function and then have deconvolution ready to go. So I'm going to go ahead and run it. And here it's creating the luminance mask. Now it's running StarNet, and what StarNet will do is scan the entire image and use machine learning, basically a neurological network. And through that machine learning, it actually understands how to isolate the stars in the image and pulls those out. So we'll let that run. Okay, so the script has generated the star mask and basically is just generating deconvolution, deconvolution support. You can see that in the progress down here as it's running. This is updated. Once that mask is done, it should be pretty much ready to go. So we're gonna see that, and sure enough, it's popped up. So here's what's happened. There's a deconvolution dialog that's ready to go. It's just waiting for the point spread function, and it's launched the dynamic point spread function. So what we do here is we use this non-stretched luminance channel to identify stars, and we just simply click on them. Now you'll notice some of these are red. The reason why they're red is because we created what's called a binary mask that cuts off the higher intensity channels. We don't want what's called oversaturated stars to go into our point spread function because that'll throw the model off. So this highlights the stars that are oversaturated so that I know not to click on them, and instead I pick other stars. Now, there's an art to point spread function. A lot of people do certain types of sorts and filtering and everything else, and they recommend keeping it to one category of star. I tend to be more simplistic, and I seem to get good results just by eyeballing the stars. I try to find representative sample. I'm not getting stars that are super small. I'm not getting stars that are super large. And I usually shoot for about 40 of these stars. And so what I'll do is stop the recording and continue clicking, and then we'll go from there. Okay, I'm back and I've picked about 41 stars. So that's the whole purpose of this tile, is just to generate it. So now that I've picked them all, I'm not going to sort and filter or do anything. I'm just going to select them and click on this camera. And what that'll do is generate a new image that is our point spread function. And you can see the preview here of what that looks like. So that one was pretty round. I've had them very elliptical. I can close this because I'm done creating the point spread. I can also go ahead and close this image out, as well as this was the mask that was overlaid on it. So we can close that. Now we're ready to do deconvolution. So this is an iterative process. We start on a sample, see how it turns out, and then apply to the whole. So I've got a preview that covers a good sample of stars. Let's go ahead and apply the star mask. And we can see certain stars are protected, but it does have a cutoff, so the really large stars didn't get pulled into the star mask, which is fine because they probably wouldn't handle deconvolution well anyway. So I'm going to go ahead and pick the PSF that was generated, the point spread function. Now it's selected. Everything else has been pre-filled out by the script. We do what's called deringing. I'll talk more about that. We do local support, etc. So we're going to run this. It's going to do 25 iterations. And what we can see is if you look at these stars, they've tightened up a little bit. They've got a bit of a ring around them. Let's see if I can zoom in and show you so you can see kind of the color. But if I toggle back using this preview button, you can see loose, tight, loose, tight. So the deconvolution tightened them. Now for those rings, what I can do is in deringing, this global dark is at 0.002. So I'm going to increase it, in fact, quite a bit to 0.01. So we'll increase that global dark, and then I'm going to just rerun this. Previews always reset when you apply an action to them. That's why they're so useful for trying things. Now we can see they've tightened, but the rings are not as prominent. So again, I'm toggling. It's probably pretty subtle in the video. but it's good enough for me. Now let's take a look at what this would look like if we didn't de-ring it at all. So I'm going to just completely uncheck that and run that to show you why de-ringing. So I don't know if you saw that, but these have really sharp rings around them of weird colors. So that's an issue if you don't have that. That's why we put that on. And then the other thing that I want to point out is what would happen if we didn't have a star mask. So I'm going to just disable the mask. And we're going to run this again. So that's what happens with no mask. That's why a good star mask is so important, because it tries to deconvolute everything. So we're going to put this back, de-ringing. We're going to enable the mask. We're going to test this on the preview one more time. Looks good. We'll go to the full image, apply that there, and I will be back once it's done doing its 25 iterations, which will probably take a couple minutes on this computer.